So in class, we proved this theorem, which describes the open and closed subsets of a metric subspace of a metric space. All right, so if Y is a metric subspace of X with its subspace metric, and E is a subset of Y, then the theorem said that E gets to be open relative to Y, in other words, open in the metric subspace Y with its subspace metric, if and only if E is the intersection of an open subset V of X with Y. All right, so E is open if and only if it's the intersection of an open subset V of X with Y. And E gets to be a closed subset of Y, or closed relative to Y, if and only if E is the intersection of a closed subset F of X with Y. So what is this saying? It's saying that the open subsets of a metric subspace are precisely the open subsets of the full space with the metric subspace Y, and the closed subsets of Y are exactly the intersections of closed subsets F of X with Y. Okay, well, using this theorem, we want to give some examples of open and closed subsets of a metric subspace of the real line with, of course, the Euclidean metric. Okay, so specifically, let's take Y to be equal to this half open interval, so close 0, open 1, viewed as a metric subspace of the real line with its usual Euclidean metric. All right, so here's a picture of Y sitting as a subset of the real line. Then we claim that E, this interval here, so closed 0, open 1/2, is actually open relative to Y. And how can we show that? Well, if E is open relative to Y, then by the theorem above, we would be able to write E as the intersection of an open subset of the entire real line with Y. Okay, so let's take a look. So this is what our subset E looks like. So here's E right here. And as we said, we can say that this E is open in our subspace Y if we can write it as the intersection of an open subset of the real line with Y. And in fact, you can see that if you took V to equal the open interval minus 1/2, 1/2, this is going to be open in R, and if we intersect this V here with Y, which looks like this, what we're going to be left with is our set E. So E is indeed the intersection of an open subset of the entire real line, in other words, our full metric space, with our subspace Y, and therefore E is open relative to Y. So let's write that down. So E is open relative to Y because V equal to minus 1/2, 1/2 is open in R. Well, for example, V is actually the 1/2 neighborhood about 0 taken over all of R. So we can write this as N D0 1/2. All right. And So that V is open, and E is equal to V intersected with R. Okay, so what did we show? We showed that this set here is open in Y. On the other hand, it certainly doesn't look open in R. So let's write that down. So, however, we should note E is not open in R. Well, for example, because, well, 0 is in E, right? 0 is in E. There it is. But no epsilon neighborhood about 0 is going to be contained in E if we take the epsilon neighborhood in R. But for any epsilon greater than 0, we can say that we take the epsilon neighborhood about 0, and this is in all of R, so this looks like minus epsilon, epsilon. So this is the epsilon neighborhood in our original metric space R using the notation we introduced in class. This is certainly not going to be contained in this interval here, which is E. So, therefore, we can say that E is not open. If E were open in R, of course, because 0 is in E, we would be able to find an epsilon neighborhood about 0 contained in E, and we're not able to do that. That should not be a contained in, that should be a not contained in, clearly, as I said. Okay, so what can we conclude? Being open in the subspace is not necessarily the same thing as being open in our full space. And also, while we have very good intuition about what an open subset of the real line looks like, we kind of have to throw out some of that intuition when we're thinking about open subsets of a submetric space. All right, now let's give an example of a closed subset of this metric space. So again, we're taking Y to be equal to the interval of all real numbers greater than or equal to 0 and less than 1. And we're saying that E is equal to this half closed, half open interval. 1/2 to 1 is actually closed relative to Y. And why is that? Well, according to our theorem, E is going to be closed relative to Y if we can write it as the intersection of a closed subset of our full metric space, which is to say a closed subset of the real line with its usual Euclidean metric, and Y. Okay, so can we do that? Well, let's take a look. So here is E. It looks like half closed, 1/2 to 1. All right, so this is our E right here. And you can ask, well, could we write this E here as the intersection of a closed subset of the full real line with Y? And yes, we could if we took F to be equal to this closed interval now from 1/2 to 1. So there's F right there. So F is supposed to be the closed interval 1/2 to 1, and we intersect that closed interval with Y. What are we going to get? We're just going to get E back. And that, according to our theorem, says that E is closed in Y. So let's write that down. So E is closed relative to y because the set F equal to 1/2 to 1 is closed in R. We're good at recognizing closed subsets of the real line now. Is closed in R. And if we intersect this F with our Y, we're just going to get E back. Okay, so this set E is actually closed relative to Y. However, if we think of this as a subset of the entire real line, it certainly doesn't look closed to us as a subset of the entire real line. So let's just note that as well. However, E equal to closed 1/2 open 1 is not closed in R with its usual Euclidean metric because, well, for example, one is going to be a limit point in E. If we take the set of limit points in R, i.e. 1 is a limit point of E taken in R, because any epsilon neighborhood about 1 taken in R is certainly going to intersect E at a point other than 1, but 1 is not in E. And so E is not actually closed in R. If it were closed in R, each of its limit points taken in R would actually be in E. All right, so what do we have then? We have, just to recap, this E is closed relative to Y, but it's not closed in R. So being closed in the subspace isn't necessarily the same thing as being closed in your full space. So when dealing with subspaces, again, we need to throw out some of our intuition about what it means to be closed in the subspace. And that's all. Finally, here's an exercise for you. So now let Y equal the union of this interval with this interval here in R with the Euclidean topology, and show that this set E is both open and closed relative to Y. And the question is E open or closed relative to R? And then finally, can you give another example of a set that is both open and closed in Y?